This chapter deals with thermodynamics, entropy, enthalpy, and free energy. The goals of this chapter are to understand the term entropy, which is abbreviated S, or S of naught, that naught means under standard state conditions, or change in entropy, that delta symbol means changing, usually it's final minus initial, or the change in entropy at standard state conditions. Another goal of this chapter is to understand processes that are spontaneous versus non-spontaneous processes, including spontaneous and non-spontaneous reactions. An introduction of another thermodynamic term will be done in this chapter, and that is delta G, which stands for Gibbs free energy. It's the change in free energy, and also you can have it under standard state conditions. The ultimate arbiter of whether a reaction is spontaneous or not is delta G, but it has contributions from delta H and delta S, as well as the temperature. So we want to know this equation and know how delta H, which we studied before, enthalpy, heat flow, or change in enthalpy because of the delta H. And we will talk about the change in entropy, order or disorder, how those, along with temperature, contribute towards delta G, Gibbs free energy. Same situation, same equation, we can also have it under standard state conditions. Typically, standard state conditions are 1 atmosphere of pressure and 25 degrees C. And if you're dealing with a reaction that has aqueous solutions, typically the concentration of the reactants is 1 molar. Delta G, which is Gibbs free energy, it is the energy that is capable of doing work. It is not energy that's wasted as heat. But this is real energy. There's a relationship between delta G and the equilibrium constant K, so free energy is related to reactions that are in equilibrium, and the reactions are shown, the relationship is shown here, the free energy with situations that involve Q and situations that involve the equilibrium constant K. So delta G equals delta H minus T delta S is an important equation to know in this chapter. And delta G ultimately decides whether the reaction is going to be exergonic. In that case, the value of delta G is negative, or endergonic. In that case, the reaction has a sign of positive, or it's a positive value of delta G. So it's an energy, so it's usually in kilojoules per mole or joules per mole. And the contributions towards delta G are done by delta H, which we've studied before is enthalpy, a heat flow. If delta H is positive, then the reaction is endothermic. If delta H is negative, the reaction is exothermic. Heat is given from the system to the surroundings in an exothermic reaction. And then entropy, which is a measurement of order or disorder. Does the reaction proceed toward more order, or does the reaction proceed towards more disorder? So more disorder than S or delta S, the change in entropy is positive. If it's less disorder, if there's more order that's being produced in the products, then the value of delta S or S will be negative. So whether this is positive or negative, whether this is positive or negative, and whether your temperature is high or low in the reaction will tell you whether delta G is positive or negative. Ultimately will tell you whether the reaction is going to be spontaneous, exergonic, negative value of delta G, or endergonic, a positive value of delta G. Also, the same situation also occurs under standard state conditions as well. So the ultimate contributor towards whether a reaction is spontaneous or not is enthalpy, entropy, as well as temperature. Another important aspect of this chapter is the relationship between Gibbs free energy, Q, and the equilibrium constant K. So these are two equations that you should familiarize yourself with. The free energy of a reaction under non-standard state conditions really depends on the free energy of the reactions at standard state conditions. We can get these values from the back of a book. This is the sum of the products minus the sum of their reactants, plus the natural log of Q times RT. R is the gas constant, 8.314. T, temperatures in Kelvin. So remember what Q is. We use Q to determine whether our reaction is in equilibrium or not. If Q equals K, then we are in an equilibrium, and then your delta G is equal to 0. So Your delta G is 0 if the reaction is in equilibrium because it's not going in any one particular direction. It's not favoring the products and it's not favoring the reactants. It's just delta G under standard state conditions. If Q is greater than K or if Q is less than K, then you can use the alligator rule to determine which way the reaction will proceed. So the relationship between delta G, K, as well as Q, if we are not under equilibrium considerations, not in equilibrium concentrations, this is the relationship. The interrelationship between these three, Q, K, and delta G, whether standard state or non-standard state, all of them are interrelated. The first thermodynamic parameter that we want to talk about is entropy, and entropy is a measurement of disorder. Now, before we even talk about disorder and order, let's take a look at processes that are spontaneous or non-spontaneous. This is also implicated in our discussion of entropy. So if you take a look at this first example up above, you have a gas on the left-hand side of the bulb. If you open the knob, the gas will diffuse. So that is considered a spontaneous process because the gases are going to move from this area on the left to this area on the right. That just happens on its own volition. What does not happen is that the gases all of a sudden decide to segregate and partition indiscriminately. So gases really just do not behave in a way where they separate from one another, or all gas molecules decide to just move from one side to the other. So gases don't pick and choose, they diffuse, and their motion is random. So shown here at the bottom is what would be considered a non-spontaneous process. So entropy really has to do not just with spontaneity or non-spontaneity, it has to do with order or disorder. So this is a situation that goes from order to disorder. That's usually how most reactions proceed, though some reactions go the other way. You can get from disorder to order. But in order for that to happen, that's usually a non-spontaneous reaction, and that requires an input of energy. So we define entropy as a measurement of disorder. We also define the fact that some processes are spontaneous versus others that are spontaneous. So notice that I'm talking about S and entropy, a term that we will define later in these notes. We also should recognize other thermodynamic parameters, particularly enthalpy, which is what we studied in this course previously, having to do with whether a reaction evolves heat, that specific form of energy, or whether a reaction requires heat, requiring it usually from the surroundings. So this is one parameter, entropy is another parameter, temperature is another parameter. All these things come together and contribute towards the Gibbs free energy to make a reaction either go or not go. So this is just basically telling us that enthalpy and this term S or delta S, entropy, they are independent of one another. So you can have a reaction that's exothermic by virtue of the delta H. So that delta H naught symbol tells you that it is under standard state conditions. And all of these are under standard state conditions. The first two reactions are exothermic, so they will release heat to the surroundings. And the last two reactions are endothermic, so they require heat. But all four reactions, regardless of whether they're exothermic or endothermic, will happen spontaneously. That is, all of these reactions are going to go. Left to their own devices, H2O solid will go to H2O liquid. Left to its own devices, H plus OH minus will give you water. Left to its own devices, methane and oxygen will combust. And left to its own devices, ammonium nitrate dissolved in water will dissociate into its individual ions. So that's what we define as spontaneity. Now in terms of entropy, order, you can see here that some reactions will give disorder. So going from a solid to a liquid. A solid is relatively ordered in its atomic arrangements. Liquids are not that ordered in its atomic arrangements, so this would be entropically favored, more disorder. In fact, all of these, hence being spontaneous reactions, all of these have an increase in entropy, S or delta S associated with them. So this is one of the more important equations in this chapter that you should get to know. It has to do with delta G. This is our final judge, delta G, and delta G stands for Gibbs free energy. And Gibbs free energy tells us that it's energy that is evolved and that is useful energy. So do not confuse that with wasted energy that's in the form of heat, which is associated with delta H, or the enthalpy of a reaction. Gibbs free energy is energy that can be harnessed. Gibbs free energy is useful energy. Gibbs free energy, if you're a cell, is energy that can be utilized to power another reaction or to move a cilia or for motility. So this is useful energy. So useful energy has components and contributors of enthalpy, temperature, and then entropy. So we're going to talk about entropy now. So as stated before, entropy is a measurement of disorder. It has a symbol S, and that S can be standalone. So that's an important point. The S can be just S, or we could go and have delta S, that is the change in entropy of a system. S is positive, means we have more disorder. So remember, signs are important. A positive value for S or delta S means that you're moving towards disorder. So what is disorder? Disorder basically means more motion, more degrees of freedom. So in chemistry, we deal with molecules. Molecules can rotate. Molecules can vibrate. You can measure vibrations of individual molecules using infrared spectroscopy. Molecules can move left or right. Bonds can rotate. All of these things sort of come under the category of disorder. Another thing that causes disorder is more mass, taking out more space, spreading out, the ability to just move and not be ordered. So in the grand scale of things, generally speaking, the entropy of a solid, remember it's very ordered, it's lattice-like, is very, very low. So we would have negative values or very low values. The entropy of a liquid, it would be kind of intermediate in values. The enthalpy of a gas would have the highest amount of disorder, highest amount of entropy, and more positive value if we were to assign a number. You can see, look at the molecular arrangement here. A solid, this is very ordered, very compact. A lot of solids are arranged in a three-dimensional array. Solids have atoms that are packed in unit cells. They have an edge length. We study this in the lab involving densities. And liquids, yeah, they're kind of more spread out. They have more motion to them. And then you want to go to another level of disorder, a higher level of entropy. You can talk about vapor or gas. More disorders involved when you mix a solute with a solvent and to get a solution. So things are more spread out, things have more space. So all of these issues, all of these phenomena lead to an increase in entropy. Now, an important point that's worth reiterating is that S can be standalone, or S can be the change in. So we can calculate the change in entropy of a reaction. Just like in previous chapters, we calculated the change in entropy of a reaction and use that positive value or negative value to determine whether the reaction is exothermic or endothermic. Standard entropy are values that you find in the back of a textbook. These are values that are generated at standard state conditions, almost unilaterally at 1 atmosphere of pressure, 25 degrees C. Some textbooks, if you're dealing with an aqueous solution, the concentration of that would be 1 molar. And so these typify standard state, and they have a not symbol associated with them. Worth looking at units. Usually the units are joules over Kelvin, or if you're dealing with it on a per mole basis, like for 1 mole of the entropy of 1 mole of a substance, it's joules per Kelvin per mole. So what's different between the standard enthalpy of formation versus the standard entropy? Both are under standard state conditions, but the standard enthalpy of formation for elements in their most naturally abundant state, natural abundance, the standard enthalpy of formation is 0. The standard entropy of formation, or the entropy by itself, is not 0. So take a look at this table here that I copied from a textbook. or I copied and pasted from a textbook. Br2 gas, the standard entropy of formation of that is actually going to be 0 because bromine in its natural abundant state will be diatomic and would be a gas. So the standard enthalpy of formation is 0, but the entropy, the standard entropy for 1 mole of Br2 gas is not 0. So that's a very unique distinction. You're going to find non-zero values, and this is the entropy associated in making a Br2 gas molecule. It's worth noting that we are talking about S here, and the values in the back of your textbook are S, but you can also calculate delta S, and if that reaction is in standard state, you can talk about delta S naught, or the change in entropy of a reaction under standard state. Most of these values are in the back of a textbook. We do not memorize them. One thing that I would like for you to be aware of is the units here, joules over Kelvin times mole, if you're talking about 1 mole of a substance. Important denotion about signage. If you are a positive value for your S or delta S, that means you're generating more order, and that reaction will be spontaneous. Now, that reaction may or may not be spontaneous. The process is spontaneous. The ultimate decider of whether or not a reaction is going to be spontaneous or will go is delta G, but this is a contributor. You can have a situation where your delta S is spontaneous, your delta H is endothermic. It could still be a spontaneous reaction or a non-spontaneous reaction, because remember, delta S and delta H come together along with temperature to determine the delta G whether the reaction is going to be a go or a no-go. Negative signs of delta S imply the process is not spontaneous. And again, non-spontaneous process is different than a non-spontaneous reaction. You could have a scenario where you have a negative value for delta S, and the reaction can be exothermic, and the reaction will still be spontaneous simply because of the overwhelming contribution of enthalpy, also the contribution of temperature. So we want to discriminate between a process being spontaneous versus the overall reaction being spontaneous, the overall reaction being go or no-go, the overall reaction going to products, or the overall reaction staying in the reactant side. Delta G is the final judge of all of that. All right, let's do some example problems. What is the entropy change for the following processes? So notice we're talking about an entropy change, so it's delta S. We could also be talking about S. Condensing water vapor. This condensation is water going from the solid state to a liquid state. And going from solid to liquid is more disorder. We would expect a positive value for the entropy. Forming crystals from supersaturated solution. Crystals are very ordered. So if you know that crystals are very ordered, crystals have very tight packing of their atoms. So when you're forming crystals, you're forming something that's more ordered than its predecessor. So this would have a negative entropy. We would expect the delta S in this change, final minus initial, to be negative. All right, heating hydrogen gas from 60 degrees to 80 degrees. Heat causes more thermomolecular motion. Heat increases kinetic energy. Heat makes the molecules spin. Rotational energy, vibrational energy, they expand, they occupy more space. Yeah, this is definitely a process that incurs more disorder. It's a spontaneous process. The entropy should increase. Sublimation. Sublimation is the formation of a solid to a gas. So solid is ordered, gas is disordered, so the entropy or the change in entropy of the system will be positive. What about reactions? So let's look at the entropy change for the following reactions. I2 solid going to 2 moles of I gas. Okay, solid to a gas. Look at the states. And looking at the states going from a solid to a gas, yes, that's more disorder. That's an increase in entropy. How about part B? Here we have now solid is ordered, a gas is disordered, relatively speaking, and then we're making 2 moles of a zinc oxide solid. So we're making a solid here, but we also have a gas here. Product-wise, we're going from something that's ordered, some disorder, and we're making something ordered. So the delta S is going to be negative. We're forming a solid. We're making something more ordered than the predecessor. And this reaction would have a negative value for the entropy change. Finally, let's look at here. Look at the states. We have a gas here. We have another gas, and then we have another gas. We have 2 moles of gas on the reactant side, 2 moles of gas on the product side. This is indeterminate. So that can also be possible that you have an indeterminate entropy change. Talk about the second law of thermodynamics. Just stated very easily, the change in entropy of the universe increases. So universe is heading towards an increase in entropy. For a spontaneous process, the system and surroundings will have an increase in entropy. And for an equilibrium process, it equals 0. For a non-spontaneous process, the system and the surroundings, their entropy contributions will be less than 0. And it's the entropy of the universe will be positive. So just like as we dealt with the situation with enthalpy, it's the exact same situation for entropy. We can compute the change of entropy of a reaction. So this knot tells us that we are measuring these values in standard state. So typically we can get these values from the back of a book. We sum the products, we sum the reactants, we subtract products minus the reactants. Each compound is multiplied by its stoichiometric coefficient. So if there's 2 moles of a product, we multiply that value by 2. If there's 3 moles, we multiply that value of entropy by 3. So here are some examples where you can compute the entropy change. This is at standard state, 1 atmosphere, 25 degrees C. And these are values that I got from the back of a chemistry textbook. So doing this, let's look at our first practice problem here. So here we have 3 moles of a gas going to 2 moles of a gas. So we would expect more order, less disorder. And that particular value here is 1 minus 173.47 as the answer. So how did we get and arrive at such a value? Well, products minus reactants. So I took 2 times CO2 gas, shown right here, and minus the sum of the reactants. So 2 times CO, here's my CO value. And don't forget to multiply by 2 plus the entropy for oxygen gas, and that's 205.03. And I multiplied it by 1 because there's only 1 mole. So doing that, products minus the reactants, each one multiplied by their stoichiometric coefficient, you get a value of minus 173.47. Okay, make sure you know and put down the proper units. This is a non-spontaneous reaction. You can tell, right? 3 moles of a gas on the reactant side, 2 moles of a gas on the product side. We're getting towards more order, and the negative sign reflects that. Same thing here, 3 moles of oxygen gas going to 2 moles of O3 gas. O3 gas is known as ozone. So products minus reactants, each one multiplied by their stoichiometric coefficient. So don't forget to multiply the value by the stoichiometric coefficient. And so I multiplied 2 times 238.82 minus 3 times O2 gas. That value is 205.03. And just as we've seen before, the negative sign tells us that we're heading more towards order rather than disorder. Okay. In this reaction, a solid is being converted to a solid, liquid, and a gas. So the liquid and the gas represent more disorder than a solid. And we're making a liquid, we're making a gas. We're having 2 moles of a liquid. 1 mole of a liquid, 1 mole of a gas, 1 mole of a solid. 2 moles of a solid are being transformed to 1 mole of a solid. So hopefully you can see here that we're reducing the number of moles of the solid, we're making a liquid, we're making a gas, and we're having more disorder. So it's reflected by this positive value, 215.39, and the entropy is going to increase. One thing I do want to tell you, products minus reactants. H2O liquid has a value that's different than H2O gas. Okay, so states are important here. So some students, or anybody for that matter, can put in the value of H2O gas, and that's not the correct value that you want to put. This problem stipulates that H2O is in the liquid state, so you want to pick the value of H2O in the liquid state for its entropy. So same situation you calculated for enthalpy. There we determine whether it's exothermic or endothermic. Here we're determining whether the process is going more towards disorder or more towards order. Now here we have a reaction, part C, that's going towards more disorder. A and B, we're generating more order as we go from reactants to products. Here we have a paragraph relating the delta S of the surroundings to the enthalpy of the system. So remember, if your delta H is negative, that is an exothermic reaction. But this fraction becomes positive. So your delta S of the surroundings actually becomes positive. If this delta H of the system is positive, it's an endothermic reaction. That means this fraction becomes negative, and that means your delta S of the surroundings becomes negative, which means the surroundings actually input more energy in, enthalpically speaking, but entropically speaking, they're becoming more ordered. All right? Now, if you do this reaction at a high temperature, this fraction is going to get lowered, so your delta S of the surroundings is going to get lowered. So you have a low value of the delta S of surroundings. That means you're going to have more disorder, less order. If you do this reaction at a low temperature, that means this fraction at a low temperature, this fraction is high, and your delta S of surroundings is going to be high, so that is more entropically favored. Here you're going to have, at a high temperature, you're going to have more disorder, less order. So there is a relationship between an exothermic and endothermic reaction and the order and disorder of the surroundings. Okay, so here we're talking about the order and disorder of the surroundings. I'll highlight that in green, versus whether the system of the reaction is endothermic or exothermic. I'll highlight that in purple. So the surroundings can increase in order, okay, or the surroundings can decrease in order and become more ordered, less disordered. So this actually is explained here in these paragraphs. Again, exothermic reaction. This delta H is negative, the surroundings become positive, so that means there's more disorder to the surroundings. If your delta H of the reaction is endothermic, that means this fraction is negative, the delta S of the surroundings become negative, that means more order, less disorder. High temperature, this reaction is low, the delta S of the surroundings becomes low, that means more order. If the temperature is very low, this fraction is high, the delta S of the surroundings is high, that's more disorder. A quick statement on the third law of thermodynamics. The entropy of a pure crystalline substance is zero. So that is where molecular motion actually ceases to exist. And where molecular motion ceases to exist, that's absolute zero, 0 Kelvin. And you have no molecular motion. So that and only that situation is where S is equal to 0 at standard state, or even at no standard state. This is a phenomenon that's very hard to achieve because molecules like to move, molecules have motion, and however, this is what the third law of thermodynamics states, that molecular motion, rotational, translational, vibrational, diffusion, if you're a gas, all of that ceases at absolute zero. The best substance that typifies that would be a pure crystalline solid, which is very hard to get. Some things do have a lot of impurities in them naturally or even synthesized. So that's all we're going to mention about the third law of thermodynamics. All right, an important section here having to do with Gibbs free energy. Here we're talking about the final judge, the final arbiter. That final arbiter is this delta G. This is what I like to call useful energy. Unlike enthalpy, which is heat flow, Gibbs free energy, delta G, it's measured as a change from final to initial or products to reactants. That change will not be lost as heat. It's good energy, energy that can be utilized for work. That's a very important distinction to make. So Gibbs free energy is energy that can be utilized for work. Just as we computed previously for entropy, and we've done previously for enthalpy in chemistry 1, we can talk about the delta G of a reaction. Now here that little knot tells us we're dealing with standard state, which is about 25 degrees C, actually is 25 degrees C and 1 atmosphere of pressure. It's the sum of the products minus the sum of the reactants, each one multiplied by their stoichiometric coefficients. So signs are important here. If the delta G, even if you're at standard state or non-standard state, if your delta G is negative, that means you have what's called an exergonic reaction. Okay, exergonic reaction. And exergonic basically means it goes in the forward direction. The reaction is forward. The reaction is a go. If delta G is equal to 0, the reaction is not exergonic and it's not endergonic. So really the reaction does not favor reactants, nor does it favor the products. If this is an equilibrium reaction and you have a delta G equal to 0, that means for every forward reaction, there's a back reaction that's happening. Finally, if your delta G is positive, that means it's non-spontaneous in the forward direction, and the reaction is non-spontaneous. We also call that endergonic, and the reaction is endergonic. Now, if it's non-spontaneous in the forward direction, in the reverse direction, it is spontaneous. So the reaction is a no-go in the forward direction. The reaction is a go in the opposite direction. Kind of like enthalpy. An endothermic reaction is endothermic. If you flip it, it becomes exothermic. Conversely, if the reaction is exothermic, if you flip the reaction, it now becomes endothermic. Here's the relationship between delta G equals delta H minus T delta S. Now this is at standard state. You can have it also not at standard state. Look at the importance of temperature in this relationship. If your delta H is negative, that's negative, and your delta S is positive, positive. So negative and negative. So your delta G is always negative, always spontaneous. It's always exergonic regardless of temperature. If your delta H is positive and your delta S is negative, so positive, negative, and negative make it positive. So your delta G is positive regardless of temperature. This reaction, delta G, is endergonic, and it's not spontaneous in the forward direction. Take a look at what happens here. If your delta H is positive and your delta S is positive, so you have a positive and negative with a positive is negative. However, if your temperature is low enough, you can still get this to be positive. If your T is overwhelmingly high enough, the negative with the high T and the negative and the positive delta S makes this negative. So here we have a temperature dependence. So here you can make the temperature, at high temperatures, the reaction is exergonic. So if you want to make the reaction spontaneous, you raise the temperature. Now look at this fourth criteria. If your delta H is negative, your delta S is negative, so we have a negative, negative, and a negative. So a negative with a positive. So if you have a very low temperature, the negative prevails, and it's exergonic. Now let's say negative for delta H, negative for delta S. Your temperature is very, very high. So a negative with a very high temperature, along with a delta S that's negative, makes that positive. So this is going to be positive at high temperatures, exergonic at high temperatures. And if you want to make this reaction exergonic or spontaneous, you lower the temperature, right? So let's review. Negative delta H is that value. Negative delta S is that value. Negative times a negative is positive. So if you keep the temperature very, very low, the positive T delta S dominates. The reaction is exergonic at low temperatures. All right, some important equations that relate delta G naught, and the equilibrium constant. So notice the term here, Q. You'll be given this equation in any exam, so you do not have to memorize it. But if you remember what Q is basically used to determine whether the reaction is in equilibrium or not. You use the alligator rule, compare Q to K, and if Q is greater than K, the reaction favors the reactants. If Q is less than K, the reaction favors the products. So that is the alligator rule. And here, delta G at non-standard state conditions is equal to the delta G at standard state. So here we have to look at the values in the back of the book, plus RT natural log of Q. All right. So R is our gas constant that takes on this value. It'll be given on the exam. But we're really comparing delta G to equilibrium, and we're determining where the equilibrium will subsist. Remember, Q greater than K, the reaction is going to stay in the reactant side, okay, because the alligator jaws point to the left. Q is equal to K, then your delta G is at 0. Actually, Q is equal to K. That means your delta G is equal to 0, and you get the second equation that we will derive relating delta G naught and K. So Q equals to K, we're at equilibrium. Finally, if Q is less than K, the alligator jaws point to the right, they point to the product side, the reaction shifts to the right. So all of these are equilibriums, and they're going to shift the equilibrium until you establish equilibrium. So equilibrium, free energy, all of them are related. Q tells us what or where the reaction will proceed to get to equilibrium. It's a very important point. Q tells us where the reaction or where the equilibrium will go, to the product side or to the reactant side, in order to reestablish equilibrium, the equilibrium condition where delta G is equal to 0. Now, if we have a situation where Q equals K, we replace Q with K. K is the equilibrium constant, and we're going to get this value here. Delta G naught is equal to minus RT, natural log of K. So it's important to realize that we're talking about at equilibrium here. Okay, so we are at equilibrium, and at equilibrium, the delta G is the same as the delta G under standard state conditions. So if your K is positive, so I just made this table to tell you that if your K is positive, we know from our previous lectures that the reaction favors the product sign. And if K is positive, the natural log is positive. But looking at that negative sign here, you'll find that the delta G naught is going to be negative, so the products are favored. If K equals 1, then you're at equilibrium. For every forward reaction, there's a back reaction. And if your K is negative, the reaction actually favors the reactant side. Natural log of K is negative. Negative with that negative is positive. Delta G is positive. We know that delta G being positive is an endergonic reaction, non-spontaneous. The reactants are favored. So now we can relate K, the equilibrium constant, to delta G. And if we're not at equilibrium, we can relate K to Q and determine where the reaction will shift in order to get to equilibrium. Couple of important points here. Delta G, that sign is important. Delta G is fluctuating until it equals to 0. That's when we get equilibrium. So as stated before, the reaction will move to the reactant side or to the product side until delta G is equal to 0. That's where delta G is equal to delta G of naught. Right, let's do this practice problem here. Calculate the equilibrium constant Kp for this reaction. This reaction is ozone going to oxygen, and we have it at 25 degrees. So we quote an equilibrium constant at a specific temperature, Kp, P stands for pressure. So we got the free energy of formation of each individual molecules of these gases I got from the back of the book. So let's do the delta G of the reaction. So the delta G of the reaction is going to be products minus reactants, each one multiplied by their stoichiometric coefficient, sum the products minus summing the reactants. We get this as our value, negative. So the negative delta G tells us the reaction is exergonic. Then we'll use this relationship. Because we have a K, we don't need to compute Q, because we know that these are equilibrium values, so equilibrium values require K. And solving for K, did some math manipulation here. We solved delta G naught previously, and don't forget, it's important that you, to get the units to cancel out, you got to multiply this by 1,000 to get it to joules per mole. R is that value, T at 25 degrees is this. And so the minus from delta G naught and the minus from the RT cancel. So we get a positive value for natural log of K. Take the inverse natural log, which is E, and this is the value that I got for K. You can check my math. K has no units, so make sure you remember we don't put units for the equilibrium constant. All right, let's do another problem here. Here we have an actual reaction, all right, and we're given a K. Okay, so probably since these are gases, this will be a Kp, and we're given a temperature. We quote K at a specific temperature. And in one experiment, the initial pressures are 0.4, 0.86, and this 4.4 times 10 to the minus 3 for all of those gases. This does not look to be equilibrium values. We don't know, but for now we'll just say they could or could not be. If they are equilibrium values, then they'll equal the equilibrium constant. But for now we'll just use Q and compare it to our equilibrium constant given to us in the problem as K. And so here are the delta G values that I was able to retrieve from the back of the book. And let's figure out the delta G of the reaction. Now it's very important you recognize that we're calculating delta G. These are not standard state. This is not 1 atmosphere. This is not 25 degrees. So we're calculating delta G, not delta G naught. However, interestingly, to get to delta G non-standard state conditions, we need the values of delta G naught for these individual reactants or products. The first thing I do in this problem is to calculate Q. So products over reactants, each one raised to the power. And doing that, I got a value of 3.5 times 10 to the minus 4. Compare Q with P, so putting Q first and then relating it to K. Here's my value of K. That was given to us in the problem, 4.3 times 10 to the minus 4. 4.3 times 10 to the minus 4. And you can see that K is greater than Q. And so the reaction should favor the products because the alligator claws are pointing towards the product side. They're pointing to the right. Calculating delta G, sum of the products minus sum of the reactants, I'm getting minus 32.6. So based on the delta G, the free energy under standard state, this reaction under standard state would be exergonic. And that would be the amount of heat that would be released, or excuse me, amount of energy that would be released, not heat. Enthalpy is heat, delta G is energy, so we're not talking about heat release. Now let's figure out the delta G under these conditions. So the important thing to recognize is to convert this to joules per mole. So I did that here. That's joules per mole, minus 32,600 joules per mole. Here's your R. Our T value here is 648 Kelvin. So our temperature, we'll add 273. And natural log of Q. We already computed Q up above here. So doing all of this math on my calculator, I get a value of minus 75,471 joules per mole, or, for simplicity, minus 75.5 kilojoules per mole. So the delta G is exothermic under non-standard state conditions. The Q is less than K. Q and K tells us the reaction favors the products. So sort of we have validation and corroboration, and delta G naught is actually also exergonic. So Q is less than K, reaction favors products, and under non-standard state conditions, this reaction is exergonic, the reaction is spontaneous, the reaction favors products.